Thank you for the introduction. So I continue our discussion on P1 spectra from yesterday. So let me first briefly recap what I explained so far. So the basic setting of is given by the infinity category V, which is presentably tensor over Zariski infinity topos, Zariski sieves of anima on smooth schemes over Z. Then we defined the infinity category of P1 spectra in V to be the formal inversion of P1 pointed to P1 in V star. So we spent some time yesterday understanding this formal inversion. And for P1 spectrum E and an object in V, recall that we defined a bigraded cohomology.
What is V star?
Star, pointed objects, the category of pointed objects. Bigraded cohomology is defined the formula like this. For 2q minus p is greater or equal to 0. We will extend it to for all pq in a bit. And when x is pointed, we also the reduced cohomology is defined by the same formula but omitting plus here. And we recall that we say E is fundamental by definition if Z map admits a retroaction. Then I explained this when E is fundamental, we get a split short exact sequence. X is some object in V, and my A1 is pointed, so we take reduced cohomology. Whenever cohomologies are well defined, we have a split short exact sequence like this. This is where we left off yesterday.
So if it's A1 invariant, the first term is 0.
Yeah. So yeah, this is where we left off yesterday. So let me continue. Let me begin by some remark or some observation. So let's consider the case P minus 1 is 2n minus 1, and q minus 1 is n. And in this case, this is defined by pi 1 like this. But in this case, the first two terms is pi 2 of something. So So you see that, so it follows that this is an abelian group, not just a group. Next, let's consider the case. This is ENN X. In this case, this is pi naught of something. And the first two terms are pi 1 of something. But we have seen this, these are abelian. So a priori, in this case, is a case, this is 2n comma n. This is just an exact sequence of pointed sets. But we can prove that this set, a priori just pointed set, is bijective to the co-kernel of this group homomorphism. So let me write it as a lemma. So we have to check something, so this is not totally obvious. But so this pointed set admits a natural group structure that makes this sequence an exact sequence of abelian groups.
Do you really use that it's 2n n? That can be any.
I have, again?
Where do you use that it's 2n n specifically, not arbitrary p?
Yeah, but this is only non-obvious thing. The other ones are just groups from the beginning. Okay, now we can define EPQ for all PQ by induction by the following formula. For all PQ. This is called the bus construction. So this is somehow ad hoc construction of homotopy groups for all PQ. But under some mild assumption of, on our base category V, we can make this construction highly coherent. So this is the following theorem.
So V is a category with which properties? It has limits, finite limits and co-limits and filtered.
This is just a co-kernel of abelian groups.
I'm asking the assumptions on V.
Assumption on V. So this is a presentable infinity category, so it has all co-limits and limits.
And the tensor product in particular satisfied with one factor is the final object, and the tensor product is the final object.
Final object.
Or like the usual thing is zero tensor, something is zero.
Yeah.
So this is part of the axioms of.
Yes. This tensor product commutes with co-limits.
So zero is replaced by the initial object.
Right. But mostly I'm working on pointed case. So this is terminal and initial. So this V star is pointed category. So this initial object is the same as.
But the tensor product defined without on non-pointed things also. Okay, I'm not an expert in this. So.
Tensor product is defined, a priori defined, but probably we don't say tensor product. It's maybe technically it's called the tensor, but we could start from everything pointed things.
But you write something like in the formula with tensor. You said that sometimes you can write something without. It's always with x plus. Yes.
Yes. X is something like a scheme. So X is, yeah, you can think X is a scheme. then yeah, I think I was careful enough to put plus when reduced cohomology is defined. Okay.
And your EPQ is now only defined for fundamental E?
Oh yes, now yes, E is fundamental. Okay, so let me state the theorem. Proved by artificial intelligence. Sorry. Annala and Toni and me. Okay, so the assumption is the following. So we assume V is compactly generated for our for our main application, it's fine. Or this is for Brown representability actually. So if Brown representability holds for non-compactly generated thing, we can remove it. But I don't know. Okay, and one more assumption is this end functor preserves filters colimits. This case, of course, fine. Then let's consider the stabilization of V, usual stabilization of V, and consider the infinity looping functor. And this functor induces a map on P1 spectra. So we get an induced functor like this. And we can check this functor carries fundamental object to fundamental object. So this superscript FD means that we consider the full subcategory spanned by fundamental object. Then this induced functor is an equivalence.
So here you work with pointed things when you consider spectra.
Yeah, yes, maybe usually spectra is defined by something like take pointed and take S1 invert. Or everything I should have assumed. No, maybe I don't want to do that. But yeah, when we consider stabilization, this is a definition of stabilization. We first consider pointed objects and make S1 invertible. Okay, so in particular, given a fundamental motivic P1 spectrum E, we have a unique rift here as a fundamental P1 spectrum in this SPV. And this bus construction is recovered as by the following formula: pi 2q minus p of mapping spectrum of P1 infinity infinity minus qx. For the right hand side is of course very defined for all PQ, and this is true for all PQ. So this is something like very canonical bus delooping. So and it is very useful, as we will see. And yeah, let me briefly comment on the proof. The proof actually uses this ad hoc bus construction. And the basic idea is to show that this EPQ defined in this way forms a cohomology theory and use Brown representability to get an inverse. So this is the basic idea of the proof, and that's why we needed compactly generatedness. Okay, let's see some examples, unless there is some question on the...
Is it not enough to have like compact generation?
I'm not sure if you know Brown representability for that. It is fine.
I think we can just have presentable because this is all done on the ultra paper. Presentables.
Presentable non-stable thing for I know.
Stable.
Yeah.
So why we need this co-camera expression instead of, I mean, the first definition is EPQ?
Why we need a cocanru?
Yeah, because we already have the EPQ, right?
Yes, but only for this is only defined for 2q minus p's.
Okay, so this is.
And this is defined for all pq by using induction.
Okay, quite good. Okay, yeah.
So this is this is something classic. This is probably by Bus, and we made it very very coherent. Okay, let's see some example. So we take Zariski sieves on all quasi-coherent qcqs schemes, and to be precise, I probably kappa small for some cardinal kappa.
So Ryomei, do we know that the fundamental objects also fall from a presentable subcategory?
Maybe not in general. In some special case, we will see that. I'm gonna, I'll come back. I'll get back to that.
P is pre-shifts or shifts?
Pre-shifts. Sorry, Zariski sieves. On all qcqs schemes.
Zariski, actually shifts.
Yes, sorry for the notation.
Sorry, I just want to ask a naive question. So previous this vast looping thing, I mean, does that imply that this mapping space has an E-infinity mono, whatever, deloop already? No, I'm not invoking this stronger. I just ask whether the previous argument already strong enough to see.
I'm not sure. Yeah, I'm not sure. Okay. I'll probably omit qcqs. My scheme is always quasi-compact, quasi-separated. And then claim is we have something P1 spectrum called KGL. So this is a P1 spectrum in V which represents K theory in the following sense. So I will tell you what's the underlying telescope. So we have a canonical map to telescope, which was defined to be the limit. And you see, limit like this. And the underlying telescope is just a periodic sequence of K-theory space. Oh, this is the definition of this one. And where K is the K-theory space, so namely the group completion of the stack of vector bundle, and which is regarded as an object of V star for this V. And the structure map is given by the multiplication of the Bott element. And this is an isomorphism by P1 bundle formula of K-theory. So at least this periodic sequence defines a telescope object. And I wanted to say this is also actually commutative algebra object in this category. Okay. So some people seem to interested in how, the precise argument for representability of some cohomology theories. So let me explain the precise construction of this KGL. But intuitively, this, it may be sufficient to understand KGL as a periodic sequence like this. This is the essential datum of KGL. But anyway, let me give the precise construction. A bit technical, but okay. So now this K-theory space is an E infinity monoid of this V star, right? So we can consider module K module in V star, and let's consider the full subcategory. Spanned by K module M, such that multiplication of the Bott element is invertible, is an equivalence. This is well defined thanks to the K module structure. And this admits a left adjoint. And the K theory lives here because K theory satisfies Bott P1 periodicity. Then the point is, this is a full subcategory spanned by modules which satisfy this condition. Then the point is, pointed P1 is already invertible in this category. So which means that mod K B star P1 is the same as P1 stabilization of mod K P1 B star. But from here we have an obvious forgetful functor to SP P1V. And KGL is defined to be the image of K-theory space here. So this is a definition or construction of KGL. And this functor is symmetric monoidal. And the K-theory is an E infinity algebra object here. So this is also E infinity algebra object here.
So you're looking at modules in the telescopes category or in the
modules again?
You have this object K.
K is an object in V star.
It's in V star. And we're looking at modules in V star.
Yeah.
So is the point that this cyclic permutation homotopic to the, like K theory sees the cyclic permutation as being homotopic to the identity even though it's not?
Right. I don't know how to formulate it, but
I mean, because this claim that the P1 is invertible in that category.
This one.
It feels similar to.
Right, but we just need E infinity algebra structure to. Yes.
Okay.
Would it be sort of related or equivalent to saying like take something like non-commutative motives, which is a symmetric monodal category, and then you have a functor from schemes into there, which is symmetric monodal and inverts P1.
Yes.
So it should factor over this.
I think so. So every and yes. Okay. It was a bit technical digression, but this is how to define KGL to be. And so let's apply this theorem to this situation. Then what we have is the following categorical equivalence. So P1 spectra in sieves of spectra. This is the left-hand side of the theorem. Is equivalent to SPP1 sieves of spaces. And now we have KGL here. So we have a unique lifter here, which let me denote it also by KGL. But the point is this represents non-connective K theory. Non-connective K theory. Namely, the underlying telescope is given by a periodic sequence of non-connective K theory. So this, Okay, the point is the P1 spectra structure on K-theory is much simpler, I would say, than S1 spectrum structure, because this is just a sequence, periodic sequence of K-theory spaces, right? But the former recovers the latter via the bus delooping. This is somehow useful principle. So let's see some applications or examples. Any questions so far?
Maybe I have a stupid question, like why you prove that, I mean, that two categories equivalence and then the image by the forgot homomorphism you got like a map from K to KGL, and why you said that its image KGL represented this KCL?
Oh yeah, you can track this this construction, and then you see. You can, you have to check, but you can check the underlying telescope is given by just this way.
Okay, thank you.
Okay, so example. So consider the étale simplification factor of sieves of spectra. And we have non-connective K-theory here. And we have Selmer K-theory here. But this is not really the image of non-connective K-theory. But the infinite delooping of underlying space of Selmer K-theory is just a étale simplification of K-theory space. So this is a theorem by Krauss and Matthew. So by using this theorem plus bus delooping, we get the following. So this functor induces a map on P1 spectra. This is formal. And this, let me denote the image of this the image of KGL by this functor by KGL edge. And the claim is this represents Selmer K-theory. Namely, so the underlying telescope is just a periodic sequence of Selmer K-theory. So we could say, in other words, we could say Selmer K-theory is the étale simplification of non-connective K-theory as P1 spectra. So if you remember the P1 spectrum structure, we get by using just the étale simplification, we get the Selmer K-theory. If you don't know Selmer K-theory, you will see tomorrow, I think. Matthew's talk. Akio's talk.
Is Pizar scheme spectra the same thing as spectra, Pizar scheme?
P is... Sorry,
I should have asked a while ago. Pizar scheme spectra is the same as spectra.
Oh, yes.
P's, like for V equal Pizar scheme, spectra of V.
Yeah, sheets of spectra is the same as spectrum objects in.
Yes, yes, yes. Right. Yeah, so this is a sieve of spectra, but this is, yeah, SP. Okay, let's see another example. Some similar example. Let's consider the left-Kahn extension of Zariski local left-Kahn extension from smooth Z schemes, sieves of spectra on smooth Z schemes to all schemes. And as Eldon told us, non-connective K-theory is not left-Kahn extended from smooth algebra, smooth schemes, even Zariski locally. But again, as Eldon explained, so connective K-theory does. So left-Kahn extension, Zariski local left-Kahn extension of K-theory space is K-theory. This is a theorem by Bott. So again, by the same idea, by the same principle, by using this theorem plus Bott looping, we get that the induced map on P1 spectra carries KGL to KGL. So in KGL is probably we can say KGL is left-Kahn extended. KGL. These are very useful, super useful observations. Okay, any questions? If not, I move on to the second part. Of my course.
Sorry, can I ask something?
Yes, sure.
The statement about representability of, or rather, that some modification of KGL is the same K thing. Is it a somehow formal consequence of this theorem you mentioned about the infinite loop space plus Bott looping, or there is some work to do?
It is quite formal if you know this theorem. Okay. And Bott looping.
Quite formal or formal?
It is formal. It's because by using Bott looping, we just need to show the similar statement only for this one. And we also need Selma K-theory satisfies P1 periodicity. Okay. So it is, yeah, it is formal, I think. Okay, so any other questions? Okay, so the second part. The first part was frameworks, and now techniques in stable Motivic stable homotopy theory. And the first thing I want to explain here is blow-ups. We call elementary blow-ups. So let's excision, blow-up excision. So let's fix some base scheme, quasi-compact, quasi-separated scheme. And here is the definition. So suppose we have a Zariski sieves on smooth S schemes. And we say this satisfies elementary blow up excision EBE if the following falls. So consider the blow up diagram like this. So the exceptional divisor is Pn minus 1x. X is some schemes. Note that this is also smooth over S. And we say this satisfies elementary blow up excision if F carries this diagram to a Cartesian diagram, Cartesian square. For all x and for all n. Then let's consider the full subcategory of P is SMS spanned by the risky sieves which satisfy elementary blow-up excision. Maybe I should have written that, but maybe I will omit. Then by formal nonsense, there is a left adjoint. And I will also probably talk about later, I will talk about spectra, and but the same definition, by the same definition, we say sieves of spectra satisfies elementary blow-up excision if F carries this diagram to a Cartesian square. Okay, why we consider this thing? So here is the lemma. Pn mod Pn minus 1 is equivalent to pointed P1 to the n in P EBE SMS. So I mean more precisely, if we denote this left adjoint LEBE, then we have an LBE equivalence here. Okay, this is why we consider this elementary blow-up excision. The left-hand side is something like 2n sphere in algebraic geometry. So this should be true from the viewpoint of Motivic homotopy theory, and it is true by I mean after enforcing this excision, simple excision, we can make it precise.
And the definition of the tensor product is I probably smash product of pointed. So we regard this as a stack. So this in this category we take tensor products. So this is sieves of pointed spaces. So you take the wedge, the smash, and you
probably I could write. So this is P1 times P1 mod infinity times in P1 and infinity. This union is taken in an appropriate sense. And let me indicate the proof for the case n is 2. So in this case we have a zigzag So by P2, we take blow up at 2 points. But this blow up is the same as blow up. This is an exercise of algebraic geometry, but this is isomorphic to blow up of the origin of P1 cross P1. And by taking appropriate quotients, we get equivalence. So we have a zigzag by blow-ups like this. So this is the idea of the proof. Now let's consider this elementary blow-up excision for P1 spectra. Then the following is the guiding principle. So for P1 spectra, for oriented, I'm going to define a bit, P1 spectra, this elementary blow-up excision is equivalent to PBF, projective bundle formula. So I'm going to make it precise. This might be helpful because you might be more familiar with projective bundle formula. But for oriented object, this is exactly the same. So first, let me define the orientability in our context. So P1 spectrum, again, yeah, it can be arbitrary V as before, is orientable if the following holds. So we have a map from P1 to BGM, which classifies the line bundle O1 and take tensor product like this. And we say this is orientable if this admits a left inverse retroaction. This is an algebraic analog of complex orientability. And remark, and this is stronger than fundamentality. Note that we have a diagram like P1 sigma GM, BGM. A good exercise to construct a map here, but we have. And here's another remark. So suppose we have an P1 spectrum which is oriented. That is, it is orientable and retroaction is fixed. The other way. Fixed retroaction, fixed. So this is a datum oriented.
But fixed as a map together with a homotopy between the composite and the identity, or fixed as a homotopy class of maps, or fixed?
Just to fix homotopy class.
Okay.
Yes. And yeah, this we also denote it by P1 sigma E. Then this map induces, by taking a junction, you see this map induces map from BGM to internal mapping objects from E to shift of E in P-zar SM. And this is the first Chern class. So this is first Chern class. So if it's oriented, we get a theory of first Chern class. And then we can formulate projective van der formula. Suppose we have oriented P1 spectrum, then we say E satisfies projective van der formula. PBF, if the following holds. So we have a map. We need some shift, sorry. Sigma P1 minus I E, I to the 1 to N, 2 E to the P to Pn, given by the first Chern class like this, C101 to the I. By using the first Chern class, we get a well-defined map like this, and we say E satisfies projective van der formula if this is an isomorphism.
Does this depend on the choice of the orientations, or
it does? Yeah, a priori yes, but it does not. Good question. I'm gonna explain it, but this is, so the point is, if E is oriented, we can formulate projective van der formula.
Do we have universal oriented theory?
Yes, MGL, but I'm not gonna talk about it. So, yeah, this is a lemma or proposition I promised. So, suppose we have oriented object, then E satisfies EVE if and only if E satisfies PBF. Maybe I just defined for sieves of, I can make it more general, but let's say I only defined for this one. So then left-hand side means E is in the full subcategory SP P1, PEVE, SMS.
You mean oriented?
Oriented. Yeah, sorry, I erased oriented. Yeah, this also shows left-hand side doesn't depend on orientation. So particularly we see from this equivalence, we see projective van der formula does not depend on, this condition does not depend on the choice of orientation. This was a bit surprising, but it is. And proof sketch idea. The point is, so we prove it by induction. By induction on what? On this is PBF for Pn. Let's consider PBF for Pn, and let's consider EVE for blow up. Then the idea is induction on N. And first note that P1 PBF for P1 is automatic, is always true for P1 spectra. It was a part of the, somehow part of the definition of P1, or it follows from P1 suspension isomorphism I explained yesterday. And then use the following diagram, blow up diagram. Consider the blow up of Pn at the point. Then this blow up is a P1 bundle over Pn minus 1. So for example, if you know the homotopy type of Pn and Pn minus 1, then we get the homotopy type of this one. And yeah, the other way also. If we know homotopy type of this and this and this, we can deduce the homotopy type of this Pn. And by using this diagram, we can proceed with the induction. That's the idea. Any questions?
What did you write in the remark? The second remark on the second line of the second remark. What is the error? Is the retraction? Yes, in the previous definition.
Yes, and the previous. So.
But I didn't read what you.
Oriented. Retraction is fixed.
Okay. And this is what you call orientation.
Oriented. Yes, this retraction is called an orientation. I call orientation. Choice of retraction is an orientation. And this orientation by adjunction induces first chunk classes.
So the condition of having this isomorphism does not depend on the orientation, but the particular isomorphism might change depending on which orientation you choose.
Right, yeah. Oh, yes.
Does A1 invariance imply EBE?
P1 stably, yes. And P1 stably for oriented objects, yes. So EBE, sorry. Just yeah. We don't need stability. We need some stability. Unstably, we need some 1D looping or.
I mean, a blow up retracts onto this exception defined by A1.
But don't we need a stability? Because
your A1.
No, I mean it's an A1 bundle.
Your A1 local, and you have the risky line. Then you get 0, 0, Pn minus 1, Pn minus 1.
Right. It's because of AN.
Yeah. Okay. Thank you.
Thanks.
So the question is, we have A1 invariant in that case.
Again, sorry.
I mean, the question just is we have the A1 invariant in that case.
No, I don't think so.
What was the question? Suppose that it's satisfying A1 invariant.
Okay, the question was if A1 invariant, this is automatic or not. Yeah. And the answer seems, yeah, it's yes. Okay, so, the point of this elementary blow-up excision is, to formulate the projective bundle formula, we need some structure, right, like orientation. But we can formulate EBE, elementary blow-up excision, for free for any sieves. So that's why we use EBE for our foundations. And this is a key point of our theory, p-homotopy invariance. This is a twisted form P1 homotopy invariance. I'm going to explain it. But first, so we will work over the following category. So consider PEVE, SMS of spectra, sieves of spectra which satisfy elementary blow-up excision, and takes P1 stabilization. This is the category we use, and let me denote it by MSS. MS stands for Motivic spectrum, Motivic spectra. So this is our working category of Motivic spectra. Then the following is the theorem proved with Toni and Marc with. So this is a p-homotopy invariance theorem. So suppose we have a vector bundle on some smooth schemes of finite rank. And it can be in a vector bundle of press stack, but you could read it as just a scheme. And suppose we are given a section of the total space of E. This is a section. Then the claim is there is homotopy HS between the following two maps. So we have two maps from X to VE. One is given by the zero section, one is given by our given the section S, and take compactification, canonical compactification. Then the induced two maps are homotopic by this homotopy in our category, of course. And note that this makes sense because we have a canonical functor from PSMS, which, yeah.
So VE is the total?
VE is the total space.
Then what's infinity?
Infinity?
Oh, S.
Oh, yeah.
Yeah, the total space actually is, it depends on what you mean, but the naive total space of the vector bundle is in Grothendieck notation VF.
Grothendieck, EGA style.
Yeah, so this corresponds to the total space of the dual bundle in classical.
Corresponds to a linear map like this. Oh, yeah, this is the theorem, but let me put one more word. So we have homotopy, but this is functorial in everything. This is moreover HS is functorial in everything, S, X, E, small s. And HS is identity if S is 0. This is the statement of the theorem. Well, it makes sense, right? It doesn't? Yeah, the section is a linear map like this, or linear map. You can imagine endomorphism between two sections.
You meant big S, I think, and then it's pullback functors.
No, actually, I meant small s.
Oh, you meant small s? Oh.
I meant small s, but yeah, you mean that endomorphisms of vector bundle.
Yeah. Okay, let me give the proof of the simplest case. Let me, so namely, of the case X is S and E is O, the trivial line bundle. In this case, theorem says two maps in P1, let's say 0, 1, is homotopic in MSS. So this is a P1 homotopy invariance. And I'm going to give a proof of this this simplest case. The proof already contains the essential idea of the general case. So let's see that. So consider the matrix like this, and consider it as a automorphism of P1. And we want to show sigma is homotopic to the identity in our category. Because this matrix transfer, two points are transformed by the matrix like this, right? But I should have clarified whether we consider this as a map as a pointed map or unpointed map. And a priori, I have to prove this claim as a map of unpointed map, because this is unpointed statement. But it is enough to show it as a pointed map, because P1 plus has the decomposition. This is pointed plus infinity in MSS, because this is, by assumption, this is a stable category. So we have a decomposition like this, and this matrix sigma fixes the point at infinity. So by using this decomposition, it suffices to show this equivalence as pointed map. So this is a pointed map. And the next step is, since P1 is invertible in our MSS, by definition, it's enough to show the induced map sigma ID, every P1 is pointed, is homotopic to identity in MSS. Now we use elementary blow-up excision, and this is P2 mod P1, as I explained. By elementary blow-up excision. So it is enough to show this induced map is homotopic to the identity. Let's call sigma prime. Maybe. But we can check this sigma prime is induced by the matrix like this, 1, 1, 1, 1, 0, 0. Such a matrix. So this is an automorphism with P2. And this induces a map. It induces an automorphism of P2 mod P1, because this upper triangular matrix fixes the hyperplane at infinity. But we know this is a commutator of upper triangular matrix. And every upper triangular matrix induces an automorphism of P2 mod P1. So this equality holds in out P2 mod P1. And to say something about sigma prime, we can just consider automorphism in our category. But in our category, this is invertible. So this is just automorphism of the unit, which is always abelian, which means this is 0. Right, so this concludes the proof. This implies sigma is ID.
When you write it as a commutator, it doesn't necessarily preserve the P1 at infinity anymore? Or?
P1 infinity?
Oh, sorry, I mean, you had the sigma prime descended to a map from P2 mod P1 to P2 mod P1, but
every upper triangular matrix fixes a...
Oh, that's the part of infinity, yeah, okay.
Yeah.
Thank you, yeah.
Any other question about the proof?
So we can extend the argument to like elementary matrix.
We can extend what to element? Yes. Yeah, the general case is more complicated, but yeah, this is the essential idea using. Sorry, I don't probably, yeah. Yes, please look at our paper. Yeah. Again?
How did you come up with this proof?
Yeah. Yes, I don't know. So we wanted to actually we started from P1 homotopy invariance, and we wanted to prove it, so that's why.
So what you construct is a homotopy. So how you go to for a given section as any section, you can think of it as a map from A1 to E, from a trivial bundle to E, but still you don't have the conjunctification. It doesn't extend necessarily to the conjunctification, so you still need some word for
general case. Yes, for general case, yeah, we need more work. Yes, this is just an indication of the proof idea.
Okay, and so you write it in a commutator, you can fix the way, but still the proof only tells you that it doesn't construct a homotopy up to, I mean, it just shows that they're homotopic, but it doesn't construct the homotopy class of homotopies. And
I didn't say anything about naturality, yes.
No, you said that it is factorial.
Yes, but yes, sorry, but in the proof I didn't say anything. You are right, so I just proved that it is homotopic. So we have to work more, but let me just, yeah. Yeah, we have to work more. Okay, now let's use this p-homotopy invariance. So let's do some homotopy theory in algebraic geometry by using this theorem. And we will see homotopy theory is great. So the first example is just, we just use P1 homotopy invariance just proved. So the claim is, so we have 2 points in A1. These are not homotopic, but after taking Stucky quotient with respect to the standard GM action on A1, this is homotopic in MS. So this is probably, this is called weighted A1 invariance, homotopy invariance. And this is, as I said, this is a direct consequence of the P1 homotopy invariance, because we have a map from P1 to A1 mod GM, sending 0, 1 to 0, 1 respectively. So if you write P1 as A2 minus 0 mod GM, such a map, this is a map, this is just a projection. We have such a map. So P1 homotopy invariance immediately implies this weighted A1 homotopy invariance. Now, the corollary of this observation is the following. Suppose we have vector bundle of finite rank on S, our scheme S, and suppose GLN acts on E. In a way, the induced action of GM via diagonal is of constant weight R, non-zero constant weight R. This is assumption or setting. Then the Stucky quotient of the total space is VGLN. I mean, point mod GLN in our category. Proof. So let's consider the following map. So A1, GM, BE, GLN, BE, GLN, given by Tx. Any question? Tx to T to the R x. You see this, yeah, you can see this is well-defined map. We have a map like this, so then you just use, but let me use as a color maybe.
So what's the action are you considering on E?
What's the, some action, we suppose we have some action such that the induced action via diagonal is then by using weighted homotopy invariance, the restriction of the two map, like ID from BE mod GLN is homotopic. Right, I mean the composition is homotopic. So this means that so I will write those two maps now. So one is just identity. And one map is something like projection and zero section. And homotopy the homotopy is between identity and this composition. But this is enough to conclude because we have a section here. So this is the end of the proof.
So where do you use that the weight is non-zero?
This is not well defined if weight is zero.
What is not well defined?
This map, why it's not well defined?
What is the map? The map from A1 mod G, which map?
This one. So this carries Tx to T to the Rx.
So the action of GM on A1 has weight 1, or you can fix any positive weight but not, or negative weight but not zero weight.
Tx sending to T absolute value of R times X.
And then you have to go with the action of GL. Okay, you have to GM. No, if absolute value of R is 0, so it's still.
Sorry. This is not identity anymore. Sorry. Yeah, you are right.
What is
R if R is 0? Yeah. Wait. Oh yeah, we don't get. Sorry. We don't get to this one, right?
What is the problem?
So suppose R is 0, then this is just sending Tx to X, right? So the one of the claim is if we take the composition to the inclusion to 0, then we get a trivial map like this. If this is identity, this is not trivial map anymore. Oh, and okay, let me write one more immediate application of p-homotopy invariance. Yeah, just. So another corollary of p-homotopy invariance is the following. this map, compactification, is homotopic to the trivial map. Homotopic, this is commutative. So this is zero section, this is projection in our category. To see this, we apply p-homotopy invariance for x is an and e is on. Then we see that we have projective boundary like this over an, and we see zero section is homotopic to the diagonal section by p-homotopy invariance. Then take projection to Pn. Then one composition is just inclusion. Sorry, this is only the, maybe let me just proof of the case E is On for simplicity. Then claim is just inclusion is trivial. But from this diagram we get this statement, right? One composition is just inclusion and one composition is the trivial map. This is something nice to remember. So this says the inclusion, canonical inclusion of an to Pn is trivial in motives. Okay, let me stop here, and next my lecture is on Friday. I still have something to say on this p-homotopy invariance things. Then I will explain some applications of what we have seen so far to algebraic case theory and Motivic cohomology. Thank you.
Can I ask about this corollary? Sorry, just about the statement. So what does it say in the first line? Does it say like, what is it before? Is it something rank? Sorry, in this corollary, but the quotient by GL. No, first top. Yeah. Yeah, this corollary where you quotient by GLn. Does the rank of the vector bundle have to be n?
No,
so it says like constant rank. Is that what?
Constant rank. That's the only. Weight is. Vector bundle doesn't need to be constant rank. So I think just we need a constant weight action.
So what does it say in the first line? Just vector bundle.
Vector bundle of finite rank.
Finite rank. I see.
So, but if the weight is a locally constant function which is never zero, then it still works.
I actually am not sure. So we tried to prove it, but
no. You need either always positive, always negative. If you have mixed weights.
Do you have a counter example?
But what is the problem with the argument? It's just a local local construction of maps of stacks. You can put the R as a function of on S.
Yes.
And you still have this map.
I think so, but now again we have the same problem for calculating this composition. I think we tried that, but it didn't work. It didn't work. What is it?
What's the question?
No, wait. When weight is not constant.
But locally constant?
Locally constant.
Yeah, well, it has to be, doesn't it?
Yes. Well, I mean, it can be mixed.
Well, yeah, but like, won't we just have a disjoint union decomposition? I mean, the weight can't vary continuously. It's an integer.
Like on each
It's not an
component,
integer.
it would be constant.
It's not an integer. It's an element of a lattice.
Okay.
No.
Yeah, like
I mean that the weight is locally. No, I didn't mean this. I meant that locally it's acts by some t to the r, but the r could be a locally constant function to non-zero integers. This is the same, but the other way is locally you have a basis for which you have different weights, and if all of them are non-zero, then the argument doesn't work.
Okay, sorry. Yes, I think you are right. Yeah.
This thing is looks difficult because you don't know.
Yeah. Okay, thank you. Yeah, sorry. Yeah, I misunderstood. And the answer is yes.
So do we know this automorphism of one?
Do I know automorphism?
Yeah, what?
What is it?
Yeah. It's like middle with K theory.
Yeah, good question. I don't know. Yeah.
But in A1 setting, we know.
Yeah.
Yeah, that's good question, but we don't have any control of this group.
Yes.
Yeah. So all these discussions of all these theories imply you have this cohomology theory to be fundamental, and all these theories we will see they are always fundamental.
Yes.
Is there some ad hoc example of some non-fundamental thing in this?
Actually, I'm gonna next thing I wanted to prove is everything here is fundamental. So I was planning to prove by using this p-homotopy invariance. Everything is fundamental, but I'm getting back on Friday. Thank you.
Okay, so no further questions.